Okay, so let's do an example. Here we're going to find the potential inside and outside a spherical shell which carries a uniform charge Q. It has a radius of big R, and little r is the distance away from the center to, say, some observation point P. Okay, and Q is that total charge. And here we're going to set the reference point at infinity. So first of all, let's write down Gauss's law. So our electric field is going to be equal to 1 over 4 pi epsilon naught Q over R prime squared R hat. And we know that our electric potential V of R would be equal to minus the integral from A to B, so this is the line integral of E dot dl, where dl again is our infinitesimal displacement vector, and that is equal to dr r hat. Okay, so what do we get for points outside of the sphere? So for points outside of the sphere, little r is going to be greater than big R. And we said one of the reference points at infinity. So here we have VR will be equal to minus the integral from infinity to little r of 1 over 4 pi epsilon naught Q over R prime to be squared d R prime. Okay, so this is for outside. And what this comes down to is we have our potential outside, V of R, be equal to 1 over 4 pi epsilon naught Q over R prime between infinity and little r. So for infinity it's going to go to 0, so we have 1 over 4 pi epsilon naught by Q over R. Okay, and this is for outside. Okay, so now what about inside, where we have a little r, it's going to be less than big R. So what we're going to have to do here is split the integral up into two. We're going to have one integral which is going to go between infinity and big R, and the other integral is going to go between big R and little r. Okay, so here we have our potential V of R is equal to 1 over 4 pi epsilon naught this is a negative, by the integral from infinity to big R of Q over R prime squared dr prime minus 1 over 4 pi epsilon naught by the integral. And what happens inside is quite interesting, because we have the integral from R to little r. The electric field is 0 inside because there's no charge enclosed within that spherical shell. So this integral here in fact is 0. So this all works out extremely nicely. We can just do this integral here. And what we find for outside is V of R potential is equal to 1 over 4 pi epsilon naught by Q over big R. Okay, so in fact this just depends on the radius of our sphere. So let's plot what this would look like. Okay, so what we're going to do is going to plot as a function of R for our potential VR. And we're also going to plot it, our electric field as a function of R to see how the two vary. This is VR. And below it, we're going to do it for the electric field. Okay, so what we're going to see is for the potential, it's going to be constant inside the shell, and it's going to be proportional to Q over big R. And then after little r is equal to big R, but at the surface, it's going to decrease as 1 over R. The electric field, on the other hand, is 0 inside, and at the surface, what we're going to see is that the electric field is going to decrease as 1 over R squared. Okay. So what's important here is that the potential, as you can see, is continuous over the surface of the shell, whereas the electric field is not.